Welcome back to the Deep Dive. Today we're plunging into a topic that really makes you reevaluate, well, the very foundations of computing. Think for a moment about the most incredible, intricate, and efficient computing machine we know, the
Hmm.
human brain. It processes an astonishing, almost unimaginable amount of information. It learns new things, adapts constantly,
Mm.
and does all of this with just, well, mind-boggling efficiency. We're talking about consuming only about 20 watts of power.
Right.
That's less energy than a dim light bulb.
Hmm.
It's this organic marvel of parallel processing and integrated memory working tirelessly without a single fan or cooling unit. Just amazing.
It really is.
Now, let's contrast that with our everyday computers, the
Mm.
devices we're also familiar with. They're built on what's called the traditional von Neumann architecture.
Mm.
In this design, the central processing unit, the brain of the computer and the memory, where information is stored, they're two distinctly separate things. Imagine trying to solve a complex problem where every single piece of information you needed had to be, like, physically moved back and forth between two different rooms just to be processed or stored.
Yeah, that's a good way to put it.
This constant shuttling of data creates a fundamental problem, a real bottleneck, if you will. It's a constant struggle for speed and, crucially, for energy efficiency, especially as we try to shrink devices down to ever smaller scales and tackle more complex tasks like artificial intelligence. It's
Right.
like having perpetual rush hour traffic between your office and your library, slowing everything down and burning a lot of fuel.
That's a perfect analogy. And that's precisely where neuromorphic computing enters the picture, offering a really radical departure from that traditional model. The concept here is to move beyond the von Neumann architecture entirely. Instead, we're aiming for systems that intrinsically mimic the brain's own structure and function its parallel nature, its integrated memory and processing.
Okay.
The goal is a truly massive reduction in energy consumption, coupled with huge boosts in parallel processing capabilities. Basically, designing computers that think more like a brain and less like a sequential calculator.
So it's a real paradigm shift.
It is. This isn't just an incremental step. It's aiming for fundamentally more intelligent and efficient machines.
Okay, let's unpack this fascinating challenge then. Our mission today is to dive deep into a groundbreaking paper from 2019 by Tathagata Paul and his team. They introduced a high-performance molybdenum disulfide, or MoS₂, synaptic device.
Right, MoS₂.
And this isn't just about making faster chips or even smaller ones. It's about rethinking how computing itself works, at a foundational level, inspired by the most complex, energy-efficient system we know, the human brain.
Mm-hmm.
It's a journey into the very fabric of future technology, exploring how we can literally engineer learning into a piece of silicon and beyond. Let's start with the marvel itself, the human brain. It's truly an enigma, isn't it?
Absolutely.
Its computational architecture is so fundamentally different from anything we've managed to create with traditional silicon. Our brains don't separate processing from memory in the same way. Instead, these functions are intricately intertwined, happening concurrently and continuously.
Yeah.
This is why you can walk, talk, think, and remember all at once without your brain kind of getting bogged down.
Indeed. What's truly fascinating here is that the fundamental unit of the brain, the synapse, it isn't just a simple switch that turns signals on or off. It's this incredibly clever, tiny processing and storage unit, all rolled into one.
Okay, so it does both jobs.
Yeah. Exactly. Think of it like this. In your traditional computer, you have the CPU in one room and the memory, the hard drive, in another. Your brain. It's like every single worker has their own mini library right on their desk, constantly accessing and updating information without ever leaving their seat.
I see.
This integrated approach, where memory and computation happen at the same site, is the key to the brain's incredible energy efficiency, its massive parallelism, and its remarkable ability to learn and adapt. It allows for billions of operations to happen simultaneously with minimal energy expenditure, something our most advanced silicon-based systems simply struggle to match because they're constantly moving data around.
Right, that back and forth again. Imagine a computer that learns and adapts almost effortlessly, consuming tiny amounts of power. A machine that could process vast amounts of sensory data or run complex AI algorithms right on the device without needing to connect to the cloud.
That's the dream.
That's the dream here, the ultimate goal of neuromorphic computing. But before we get there, we have to confront the very real very stubborn limitations of our current technology.
Yeah.
That von Neumann bottleneck isn't just a technical term, it's a fundamental physical barrier, right?
Absolutely is.
It's that constant back and forth, that data transfer between the processor and memory that incessantly drains energy and drastically slows down complex
Yeah.
tasks, especially those involving massive data sets or continuous learning, like those found in advanced AI.
Mm-hmm.
It's the digital equivalent of rush hour traffic, perpetually, where instead of moving cars, we're moving electrons, and every move costs energy and time.
And this bottleneck becomes particularly problematic when we consider traditional silicon devices for the kind of highly dense, scalable, neuromorphic applications we envision. Silicon, despite its incredible history and, unparalleled success in conventional computing, is inherently plagued by significant power dissipation issues. As we miniaturize silicon transistors to pack more and more computing power into smaller areas, we run into phenomena known as short channel effects.
Short channel effects.
Essentially, at these incredibly small scales, the electrical behavior of the transistor becomes unpredictable and inefficient. Leakage currents increase, control becomes harder. These issues make traditional silicon fundamentally unsuitable for the extremely high density of artificial synapses that would be required for truly scalable neuromorphic systems. Systems that need billions, even trillions of these brain-like connections.
Wow, billions or trillions.
Yeah. So it's not just a matter of refining the technology. It's a fundamental physical barrier we need to overcome if we want to build truly brain-inspired machines that can operate with the same kind of efficiency.
So the promise of neuromorphic computing, then, is clear. To create electronic analogs of these biological synapses, to integrate processing and memory in a single unit. This isn't a new idea, you said. The vision has been around for decades. But the material science and engineering challenges have been immense.
They really have.
For a long time, it felt like we've been looking for that magic material, that ideal building block that could bridge the gap between biological efficiency and silicon's limitations, haven't we?
Absolutely. And this is exactly where new materials become not just advantageous, but absolutely essential. Ultra-thin two-dimensional materials, like the one we're discussing today, a MoS₂, emerge as a perfect candidate precisely because they offer a way to sidestep these deeply rooted problems.
That's so.
Well, their unique properties give them a natural immunity to those pesky short channel effects that plague silicon when miniaturized.
Ah.
Because they are only a few atoms thick, they also offer excellent gate coupling at nanometer-length scales, meaning we can control their electrical properties very efficiently with minimal voltage.
Okay, better control.
Right. These are critical advantages that set the stage for materials like molybdenum disulfide to truly shine. They're literally atomic-scale building blocks that can overcome some of the most stubborn physical issues in traditional electronics, opening up entirely new architectural possibilities.
Now, let's talk about the current landscape of synaptic device research. Specifically, the solutions we've been exploring up until recently. Before these new 2D materials really came onto the scene, transition metal oxides had been a popular choice, hadn't they? They seemed promising for a while.
Yes, that's true. Transition metal oxides received considerable attention in early synaptic device research. This was primarily because they can exhibit memristive properties.
Memristive.
Yeah, it means their electrical resistance depends on the history of current that has flowed through them. It offers a sort of crude form of memory.
Okay.
However, they come with significant drawbacks that have limited their practical application. For one, these oxides generally have a large band gap, which means a significant amount of energy is required to get electrons to move through them, making them less power efficient.
Got it.
More critically, they often rely on what's called ionic liquid gating to function effectively.
Ionic liquid. Sounds tricky.
It is. It means that to control their properties, you have to use a liquid electrolyte. And that inherently leads to a short device lifetime because these liquids can evaporate, degrade, or interact unpredictably with the device materials over time.
Ah. So reliability issues.
Big time. These devices are also very sensitive to environmental conditions like humidity, temperature, even atmospheric gases because of the electrochemical reactions involved in their operation. This fundamental instability and, frankly, the high power consumption raise an important question for any practical application. How do we make a truly robust, stable, and energy-efficient artificial synapse? One that can function reliably in a real-world environment over a long period without constant recalibration or specialized packaging. This long-term reliability is a major hurdle for oxides.
And that's exactly where molybdenum disulfide, or MoS₂, comes in as a potential game changer.
Mm.
It's a remarkable material from what's called the chalcogenide family.
Yep.
These are compounds often involving elements like sulfur, selenium, or tellurium, known for their unique electrical properties. Crucially, it's a solid-state solution that totally avoids all those finicky problems we just heard about with liquid gates and environmental sensitivity, offering a much more robust platform for our artificial synapses, right?
Precisely. OS2 offers a compelling, robust alternative. Compared to many oxides, it has a comparatively lower band gap.
So, more efficient electron movement.
Right, meaning electrons can move through it with less energy, leading to better power efficiency. It also demonstrates better electrical coupling to metallic gates, which gives us finer, more precise control over its behavior.
Okay.
But its advantages extend far beyond just these 2 points. It's a highly scalable semiconducting platform, which is absolutely crucial for the kind of large-scale integration we envision for neuromorphic systems. Imagine trying to build a brain with billions of synapses. You need materials that can be easily fabricated and densely packed.
Makes sense.
Furthermore, OS2 possesses a layer-dependent band gap in the visible range.
Layer dependent.
Yeah, meaning we can actually tune its optical properties by simply changing the number of atomic layers. This opens up possibilities for optoelectronic applications where light and electronics interact directly.
Interesting.
We also see respectable carrier mobility, ranging from about 1 to 30 centimeter on VOC. That's essential for efficient charge transport within the device, ensuring signals travel quickly and effectively.
Okay.
And beyond these fundamental properties, MS2 displays a fascinating array of unique transport characteristics. Things like variable range hopping, where electrons hop between localized states rather than flowing continuously, percolative switching, which describes how current paths form and break, and even valleytronic effects, which involve manipulating not just the chart of an electron, but also its quantum valley state.
Wow, okay. Valleytronics, that sounds deep.
It is. These aren't just obscure physics terms. They represent fundamental quantum properties that make MoS₂ incredibly versatile and a subject of intense research for various next-generation electronic applications. They could potentially offer new ways to encode and process information.
What's truly exciting here, though, is that MoS₂ has already shown considerable promise in high-quality, non-volatile memory cells, achieving impressive on-off ratios.
That's a key point.
This means it can reliably store information for extended periods without power and switch between states effectively. This existing track record makes it a prime candidate, almost a natural fit, for building a complete solid-state synaptic transistor. It's not just a theoretical material. It's already proven its capabilities in a closely related field, giving researchers a strong foundation to build upon.
Absolutely. It sets the stage perfectly for what Paul and his team did.
So, we've identified MoS₂ as this incredible versatile material, already proving its chops in advanced memory. But here's the twist, right? Simply having the right material isn't enough.
Not at all.
The real genius, the true innovation from Paul and his team, lies in how they engineered this material, how they built around it to create a synapse that truly sings. You see, while MoS₂ had shown promise in floating gate memory, previous attempts often needed large gate voltage pulses, sometimes up to 30 volts, just to operate.
Right, which is pretty high for low-power applications.
Exactly. Or they suffered from large energy dissipation when operated in a two-terminal mode. For brain-inspired computing where low power is paramount, these requirements are simply deal breakers. We need something much more efficient.
That's absolutely right. And this is exactly what Paul and his team addressed with their brilliant design. Their key innovation was an extended floating gate, or FG, device architecture for their MoS₂ field effect transistor, or FET.
Okay, extended floating gate, what does that mean?
Well, a field effect transistor is a fundamental building block of modern electronics, controlling current flow with an electric field. The floating gate is an electrically isolated gate used to store charge, like in flash memory. What's particularly clever about their approach is how the two-dimensional nature of MoS₂ allows it to be readily inserted into a planar floating gate architecture. Think of it like stacking atomic Legos, or creating what's called a van der Waals heterostructure.
Van der Waals, like the forces between molecules.
Exactly. Atomically thin layers are held together by these weak forces, allowing them to retain their individual properties while interacting in a precisely controlled way. In this setup, metallic layers, specifically graphene in their case, can temporarily store charge induced by a global gate. The extension part means they made this charge storage area larger.
Oh.
This design directly tackles the architectural difficulties encountered in earlier MoS₂ floating gate memory attempts, significantly improving its viability for energy-efficient neuromorphic applications by reducing the required operating voltages and energy.
So it's not just the material itself, but how you meticulously design around it, how you stack these incredibly thin layers with atomic precision, that makes all the difference. It sounds like a true feat of nanoscale engineering.
It absolutely is. The device structure they meticulously fabricated is a testament to this precision. At its core, you have mechanically exfoliated flakes of MoS₂.
Exfoliated, like peeling tape.
Kind of, yeah. It's a common technique for getting single layers of 2D materials. This MoS₂ flake serves as the active channel through which current flows, effectively acting as our artificial synapse.
Okay.
This is then layered with hexagonal boron nitride, or HBN, which acts as a crucial tunnel barrier.
The insulator layer.
Right, and then single or few-layer graphene functions as the floating gate, the memory element, where charges are temporarily stored. These core layers are all meticulously placed using a highly precise dry transfer method involving precision rotation and translation stages. This ensures perfect alignment of these atomically thin materials, minimizing defects at the interfaces.
Crucial for performance.
Very. This entire stack sits on a conventional silicon dioxide substrate. Electrical contacts are then defined using electron beam lithography, a technique that allows for patterning at nanometer scales, followed by metallization, with a thin layer of chromium for adhesion and then gold for conductivity.
Okay.
And the Crucian extended FG component is achieved by lithographically connecting that graphene floating gate layer to a much larger floating gold pad.
So that's the extension connecting it to a bigger pad.
Exactly. It's a miniature, powerful sandwich, precisely engineered down to the atomic level to control every aspect of charge flow and storage.
That level of detail is astounding. Well, let's dig into one of those layers, the HBN. Why was hexagonal boron nitride chosen as the intermediate layer? What's its critical role in this smart synapse, acting as that tunnel barrier?
The choice of HBN is absolutely vital, a real stroke of engineering insight. Its excellent dielectric properties and its single crystalline form, meaning it's a superb electrical insulator combined with a very large band gap of approximately 6 electron volts, make it an ideal material for this application.
Large band gap means good insulator.
Right. Its function is twofold. First, it allows for controlled quantum mechanical charge tunneling between the floating gate and the MoS₂ channel.
Quantum tunneling.
Yeah.
Electrons going through the barrier.
Precisely. This tunneling is the fundamental mechanism by which the device remembers or forgets, adjusting its conductance. It's like a perfectly calibrated ultra-thin membrane that only allows charge to pass under very specific conditions, maintaining precision. Simultaneously, its insulating properties significantly reduce unintentional leakage of charge, ensuring the integrity and long-term retention of the stored information within the floating gate.
So it holds the charge well.
Yes. And moreover, HBN provides a pristine, defect-free substrate for the MoS₂ channel. This is crucial for maintaining the high quality and reliability of the charge transfer mechanism, preventing parasitic scattering or trapping that would degrade performance.
So what does this all mean? It means we have fine-tuned, incredibly precise control over the flow of information, the movement of charge, within our artificial synapse, thanks to this exquisitely engineered HBN barrier. It's like having a perfectly engineered atomic scale valve that dictates how and when information is stored and retrieved, which is absolutely central to mimicking brain function.
And that precise engineering extends to what we call capacitance. The extension of the floating gate, achieved by connecting the graphene layer to that large gold pad, isn't just a minor detail. It significantly increases the total area of the underlying silicon dioxide capacitor.
Okay, bigger capacitor area.
Right. This seemingly simple change has profound effects on the device's performance. Crucially, it dramatically improves the gating efficiency.
Gating efficiency.
Meaning a smaller voltage applied to the main gate has a much stronger and more effective influence on the channel conductance.
More bang for your buck, voltage-wise.
Exactly. This improvement is reflected in key performance metrics, such as achieving an almost ideal sub-threshold swing of just 77 millivolts per decade over 4 decades of drain current.
And a low subthreshold swing is good,
Yeah.
right?
Very good. For those familiar with transistor design, you know that means the device can switch from its off state to its on state extremely sharply and efficiently. It's like having a light switch that doesn't dim gradually but snaps instantly between fully off and fully on with minimal energy. That's critical for brain-inspired systems that need to fire billions of times a second without overheating.
Makes sense.
This optimized capacitance engineering also significantly reduces the required drain bias and switching pulse voltage for stable memory action. This, in turn, leads to improved integrability with existing systems and lower electrical stress on the gate dielectric, further enhancing device longevity and reliability.
It's like designing a super efficient on-ramp for information, making the device much more responsive and power-friendly by optimizing how it feels and reacts to the gate voltage. This is a foundational step in making these artificial synapses practical for large-scale neuromorphic systems.
Absolutely fundamental.
All right, we've built this incredibly intricate device. Now, how does it actually behave electrically? The paper describes something quite specific: antihysteretic transport. Can you explain what that means in practical terms? What does it reveal about the device's memory and dynamic behavior?
Certainly. In antihysteretic transport, what we observe during an electrical sweep of the gate voltage is that the threshold voltage—
That's the voltage to turn it on.
Right. That threshold voltage is lower when we're sweeping the gate voltage upwards in the forward direction, and then it's higher when we're sweeping the gate voltage downwards in the reverse direction.
Okay, so the on-point shifts depending on which way you're going.
Exactly. This creates a distinct loop in the device's electrical characteristics, which we call a hysteresis window. What's particularly fascinating here is that this hysteresis window isn't fixed. It's strongly dependent on the range of the voltage sweep.
How so?
Well, the researchers found that this window decreased significantly from approximately 11 volts for a large sweep range of about 18 volts down to entirely hysteresis-free transport for sweep ranges below about 6 volts.
So you can control the memory effect by how wide you sweep the voltage.
Precisely. This dependency is quite telling, as it indicates a controlled and tunable memory effect. Crucially, the researchers were able to control the very center of this hysteresis window by horizontally shifting the gate voltage sweep range.
Okay.
This precise tunability allows for careful manipulation of both positive charge, meaning electron trapping, and negative charge, or hole trapping, within the floating gate. This ability to tune the threshold voltage and manipulate charge is an absolutely essential component in designing a truly power-efficient FET, especially for neuromorphic applications where adaptable response is key.
So it's like tuning a dial to control how the device remembers and forgets, or perhaps more accurately, how it dynamically shifts its on and off points based on its recent electrical history. It's not just a static switch, but one with a tunable memory built into its very operation.
Precisely. And this leads us directly to another critical benchmark of efficiency that directly relates to that dynamic tuning: the subthreshold slope.
Right, we touched on that lower is better.
Lower is much better. This metric signifies how efficiently a transistor switches from its off state to its on state. Think of it as how quickly the current increases for a small change in voltage. The comparison provided by Paul and his team is quite striking and really highlights the impact of their engineering. Devices incorporating their extended floating gate architecture achieved an almost ideal subthreshold slope of approximately 80 millivolts per decade.
Which is close to the theoretical limit, you said.
Very close for room temperature operation. In stark contrast, devices without the extended floating gate saw this slope increase significantly to about 300 millivolts per decade, much less efficient switching. Okay.
And for devices without any floating gate at all, the subthreshold slope operated at an even larger, much less efficient rate of approximately 1,000 millivolts per decade.
Wow, that's a huge difference. This is a clear, quantitative indicator that their specific capacitance engineering design using that extended floating gate makes a real, measurable difference in power performance.
Absolutely.
It translates directly to faster on-off-F transitions with far less energy input, which are both of considerable, if not paramount, importance in building practical and scalable neuromorphic applications. It shows their design isn't just theoretically sound, but delivers tangible, superior performance.
To truly grasp how this antihysteretic behavior works and why it's so efficient, let's trace the charge trapping mechanism within the device step by step. Figure 1G in the paper illustrates this well. Imagine starting with a neutral state, no voltage applied to the back gate, what we call an initial flat band condition.
Okay, starting point. Now, as we begin to increase the gate voltage, an excess of electron, or electron doping, occurs in the MoS₂ channel. What happens next is crucial. Some of these electrons, driven by the electric field, tunnel through the ultra-thin HBN barrier and get trapped in the graphene floating gate.
Okay, charge moves into the storage layer.
Right. This trapped negative charge in the floating gate effectively screens the applier gate voltage.
Screens it, like it blocks some of the effect.
Exactly. The device responds as if the gate voltage is actually lower than what we're applying. This makes the channel more conductive for a given applied voltage.
Got it.
Now, as we begin to decrease the gate bias, this stored negative charge, this screening effect, means the device remains in its on state for longer. It only returns to its off state at a more positive gate voltage than it started with.
Hence the shift in threshold voltage.
Precisely. If we continue to decrease the gate bias past zero and into negative voltages, the process reverses. Electrons then tunnel from the graphene floating gate to the MoS₂ layer. Or equivalently, you can think of positive charge, holes, accumulating on the graphene. This accumulated positive charge now effectively screens the negative gate bias.
So the screening works both ways.
Yes. This bidirectional screening of the gate voltage happening both when increasing and decreasing the voltage is what creates the observed antihysteretic transfer characteristics. Furthermore, the researchers noted that this antihysteresis is sweep rate independent, it requires an underlayer, and its range is precisely tunable. These characteristics strongly suggest a nearly relaxation-free charge transfer process between the channel and the floating gate, facilitated by the pristine crystallinity of the HBN layer and the atomically perfect van der Waals interfaces.
Relaxation-free, meaning the charge stays put reliably.
Essentially, yes. It means the charge isn't leaking or dissipating unintentionally, it's precisely controlled by the tunneling process.
So it's like the device has a built-in active memory of the voltage it's experienced. And this memory isn't passive. It dynamically influences its present electrical state. This inherent ability to remember and adjust is absolutely crucial for mimicking the adaptive learning functions of the brain rather than simply acting as a binary switch.
You've got it. That's the core mechanism.
This brings us to the very core of brain-inspired computing. Synaptic plasticity. This is the fundamental concept that biological synapses aren't static connections. They actually change their conductivity, their strength, based on the electrical pulses they receive. This dynamic adjustment is precisely how our brains learn, form memories, and adapt to new information. So for our artificial device to truly mimic learning, it needs to demonstrate this non-volatile conductance change, meaning remembering changes under pulse gate operation.
Exactly. We can think of the gate voltage as acting like the presynaptic terminal, the input signal from a preceding neuron. And the MoS₂ channel itself, whose connectivity we're measuring, functions as the synapse, the connection between neurons. The key behaviors we need to see are potentiation and depression.
Strengthening and weakening.
Right. Potentiation is an increase in the MoS₂ channel's conductance, which simulates the strengthening of a synaptic connection, making it easier for signals to pass. This is demonstrated with excitatory pulses, for example, a negative 4-volt pulse applied to the gate, as mentioned in the paper. This causes electrons to tunnel into the floating gate, increasing conductivity.
Okay.
Conversely, depression is a decrease in channel conductance, simulating the weakening of a connection. This is shown with inhibitory pulses, such as a positive 3-volt pulse, causing electrons to tunnel out of the floating gate, decreasing conductivity.
Makes sense. Excite strengthens, inhibit weakens.
Exactly. And the paper presents some very compelling findings regarding this in their experiments, shown in Figure 2. When they compared a device with their innovative extended floating gate design to one without, the difference was stark. The extended FG device showed a considerable change of approximately 80% in channel conductance after applying pulses.
80%.
Yeah. Whereas the device without the extended FG exhibited only a negligible change of about 2%.
Wow, that's night and day.
It really is. This is a clear quantitative demonstration of the effectiveness and necessity of their specific architectural design for achieving meaningful synaptic behavior. What's also crucial for practical long-term applications is the robustness of this long-term plasticity. It persists even after a large number of potentiation and depression cycles. They rigorously tested at up to approximately 105 pulses. That's 100,000 learning events without significant degradation.
That's pretty robust.
Very. And the impact of the pulses themselves is intuitive and controllable. Pulses of similar duration but larger magnitude produce a larger change in conductance. Similarly, increasing the time period or width of the pulse while keeping the magnitude the same also increases that conductance change. This tunability allows for fine control over the learning process.
This is truly where we start seeing the learning happen in the device strengthening or weakening connections, much like how neurons communicate and form memories in the brain. It's the digital, atomic scale equivalent of repetition strengthening a memory, or lack of use causing one to fade. That 80% change versus 2% really drives home the impact of their engineering.
It really does. And to put an even finer quantitative spin on this, the channel conductance variations we observe are directly attributable to the precise bidirectional tunneling of charge across that HBM layer. We can actually calculate how much charge moves. For both potentiation, using that negative 4-volt pulse, and depression, with the positive 3-volt pulse, the average charge transferred per pulse remains remarkably constant, around 2 evu10 ocoulomb per pulse. It's a tiny amount, but consistent.
Wow, that's specific.
Yeah. To help understand this intricate charge tunneling process, the researchers employed a well-established model, the Fowler-Nordheim type electric field-dependent tunneling model.
Okay, a physics model.
Right. This theoretical framework allowed them to calculate the barrier heights, which are crucial for charge transfer. They found a barrier height of 3.1 electron volts for potentiation. This process involving holes transferring from the MoS₂ to the floating gate, and 2.6 electron volts for depression, which involves electrons transferring from the floating gate to MoS₂.
Different barriers for strengthening versus weakening.
Slightly, yes. The model also yielded predicted tunneling voltages of 3.36 volts for potentiation and 2.61 volts for depression. Now here's the important part, the validation. These theoretically predicted values are strikingly similar to those obtained directly from the device's measured transfer characteristics.
How similar?
The measured values were 3.52 volts for potentiation and 2.5 volts for depression. Very close indeed.
It is close.
This strong correlation, where theory meets experiment so closely, powerfully confirms that the charge tunneling mechanism is indeed the fundamental engine for the synaptic behavior observed in these MoS₂ devices.
That's a real aha moment right there, isn't it? It's not just theory or observation. They've measured it, they've modeled it, and the numbers align almost perfectly. That kind of strong experimental and theoretical agreement provides solid, undeniable evidence for their proposed mechanism and really validates the design.
Absolutely. It gives a lot of confidence in the results.
Yeah.
Building on this robust foundation, the device also successfully demonstrates spike time-dependent plasticity, or STDP.
STDP, okay, what's that again?
This is a very common and quite sophisticated learning process in the human brain. It's where the conductivity or strength of a synapse is not just about the strength of a pulse, but critically, it's a function of the time difference between the presynaptic pulse, the input, and the postsynaptic pulse, the response.
Timing matters.
Right.
A lot.
Exactly. The device designed by Paul and his team successfully showcases both asymmetric and symmetric STDP, which are illustrated in Figure 4 of their paper. In asymmetric STDP, which is highly relevant to how biological brains learn cause and effect, if a postsynaptic pulse occurs before a presynaptic pulse, what we call a non-causal event, where the time difference, delta t, is less than 0, there's a sharp decrease in channel conductance. The connection weakens.
Okay, wrong order, weaker connection.
Right. Conversely, for causal events, where the presynaptic pulse arrives before or at the same time as the postsynaptic pulse, so delta is a 0 or positive, there's a sharp increase in conductivity. The connection strengthens.
Right, order, stronger connection. Learning the sequence.
Precisely. This is the very essence of learning from the sequence of events. The researchers observed large changes in the synaptic weight for small time differences, which is crucial for precise timing-based learning. They measured time constants for this asymmetric STDP of about 0.34 seconds for potentiation and 0.6 seconds for depression. And importantly, they noted that these are tunable, meaning we can adjust the learning speed.
Tunable learning speed, nice.
For the symmetric STDP case, the channel conductivity depends only on the absolute time difference. The order doesn't matter as much as the proximity in time. Here, the change in channel conductivity was approximately 100%, demonstrating a very robust and clear ability for spike time-dependent learning.
This is truly phenomenal. It means the device isn't just remembering, it's actually learning based on the sequence and timing of events, just like our brains do when forming new habits or recognizing patterns.
Yeah.
This capability is what makes the device suitable for both on-chip and off-chip learning scenarios, which is a massive step towards building truly autonomous and adaptive neuromorphic systems that can learn in real time within a device or be trained remotely.
It's a huge step in that direction, yes.
Now let's talk about the absolute most crucial metric for neuromorphic computing, and really for the future of all computing: energy efficiency. We started this deep dive talking about the human brain's incredible 20-watt power consumption. If we want to build machines that even remotely approach that level of efficiency, we need breakthroughs in how little energy each operation consumes.
Absolutely critical.
The energy dissipation per pulse is a key measure here. It's calculated simply by the drain current multiplied by the pulse time and the drain bias, right?
That's the basic formula, yes. E equals I times T times V.
So how does this MS2 device stack up against the brain and against other cutting-edge devices? What do they find?
The energy fields presented in the paper, particularly in Figure 5, are truly impressive and represent a significant leap forward. They report approximately 20 picojoules per pulse for 0.1 second pulses. That's already quite good.
Picojoule, that's trillionths of a joule.
Right. But what's truly remarkable, almost mind-boggling, is a minimum dissipation of approximately 5 femtojoules per pulse for pulse widths of just 1 microsecond.
Femtojoules, that's quadrillions.
Quadrillionths of a joule, yes. An incredibly tiny amount of energy. Think about that this isn't just an incremental improvement. It's potentially a fundamental shift in what's possible for power consumption in these kinds of learning systems.
5 femtojoules per synaptic event.
Yeah, this is better than previously reported two-dimensional synaptic devices. It also dramatically surpasses general synaptic device candidates like silicon FinFETs, advanced conventional transistors, and even other promising memory tech like RRAMs, resistive random access memories, which are also being explored for neuromorphic uses.
Better than RRAMs, too.
And furthermore, it outperforms even large-scale neuromorphic array processors, such as Intel's Loihi or the European Brainscales project. These are massive, dedicated neuromorphic hardware platforms.
So better than dedicated hardware.
At the single synapse level, yes, in terms of energy per event. We're talking about an energy dissipation that is about 5 orders of magnitude.
5 decades.
Yeah.
100,000 times lower.
100,000 times lower than similar devices operated in a simply two-terminal geometry and also conventional complementary MoS or CMOS devices. It's a level of efficiency that is comparable to other leading transition metal dichalcogenide or TMDC-based systems, which really reiterates the immense benefits of using these novel 2D materials for enhanced power efficiency.
What's truly fascinating here is that we have a device performing brain-like functions, mimicking complex learning like STDP, but with dramatically, almost unbelievably lower power requirements. That's not just an improvement, that's a game changer.
It really is.
Imagine a future where powerful AI isn't confined to massive, energy-guzzling data centers, but can run on a chip the size of your thumbnail, powered by a tiny battery, right inside a truly intelligent prosthetic, or an always-on personal assistant, or even a self-learning sensor network.
Exactly.
This kind of unprecedented efficiency is the key that unlocks computing everywhere, for everything, making AI truly ambient and ubiquitous, breaking free from the constraints of massive power consumption.
Indeed. This breakthrough opens up significant avenues, but as with all cutting-edge research, it also highlights areas for future development. The paper discusses several crucial next steps for the field.
Like what?
Well, for instance, improving scalability. The current implementation of those STDP protocols in these devices involves a large overhead due to the use of a multiplexer.
A multiplexer, a switching component.
Right, essentially a switch that routes signals. Reducing this overhead would significantly enhance scalability and ease of integration into current neuromorphic architectures, allowing for much denser arrays of these synapses.
Okay, packing more synapses in.
Exactly. Another exciting prospect is the potential for more holistic integration. Leveraging the knowledge that both charge and heat transport in these van der Waals heterostructures are strongly temperature dependent and can be finely tuned with external electric fields. Future designs could integrate transport layers, heating layers, and floating gates in a sophisticated bottom-up fashion. This opens up a wide range of possibilities, including the implementation of more biorealistic neuromorphic realizations, essentially, devices that mimic even more complex biological neural dynamics.
More brain-like than just SPDP.
Potentially, yes. For example, through electrothermal pulsing and what's called a second-order memristor, which can simulate even more nuanced learning and forgetting patterns found in biological brains, getting closer to the real thing.
So the paper truly provides a new framework for solid-state synaptic devices that are fundamentally free of those problematic electrochemical reactions we discussed earlier with the oxides.
That's a key takeaway. Solid state, no liquids, much more stable.
This means we're looking at a future with more stable, more reliable, and ultimately more powerful neuromorphic applications, paving the way for machines that can truly learn and adapt with unprecedented energy efficiency. It's an exciting time to be watching this field.
Absolutely. The potential is enormous.
Right.
Hashtag outro.
And what a deep dive it's been. We've just explored a charge tunneling-based synaptic transistor, meticulously engineered using ultra-thin molybdenum disulfide and hexagonal boron nitride. We've seen how this remarkable device beautifully mimics fundamental brain functions like potentiation and depression, the strengthening and weakening of neural connections, and even complex learning mechanisms such as spike time-dependent plasticity, which allows it to learn from the precise timing of events. All of this while maintaining astonishing, truly unprecedented energy efficiency. Those femtojoule numbers are just incredible.
They really are. This deep dive really underscores how the cutting edge of materials science, combined with innovative nanoscale engineering, is actively propelling us towards a future where computing is not just faster, but fundamentally smarter, more adaptive, and profoundly more energy conscious. It brings us significantly closer to achieving truly brain-like intelligence in machines, transforming not just how we interact with technology, but how technology itself can perceive, learn, and adapt to the world around it. It's about building intelligence from the atomic scale up.
So what does this all mean for you listening in? Think about it. What new frontiers, what grand challenges will be opened up when computing power becomes as energy efficient and as adaptive as the human brain itself? Imagine breakthroughs in personalized medicine where AI can learn from your unique biology in real time, or climate modeling systems that can adapt and predict with unparalleled accuracy, or even truly intuitive robotics that learn human interactions with biological finesse.
The possibilities are vast.
When the fundamental energy barrier for powerful computation is dramatically lowered, what previously impossible problems suddenly become solvable. Something to think about. Keep exploring, keep learning.